Part 2, this is for questions 11 to 20. Question 11, which statement about the molecule phosphorus pentafluoride is correct? Then option A, they are saying every fluorine to phosphorus to fluorine bond, the angle is 100 and it is 90 degrees. Let's look at the structure. So the structure of this molecule, we have phosphorus here. We are going to have 3 of them here in a in a trigonal planar structure horizontally, just like you can look at a table, okay? But now this one, we have a triangle, okay? You have a triangle here. Then there is, this is the phosphorus. Then we have one down, okay? One going in and then one going where? Facing us this way. Then there is one that is going inside there, okay? In other words, one is above the table, then the other one is below, okay? Better to say it that way. So one which is above is this one here, then one which is below is that one there. So we have the fluorine here, then here, then here, here, and here, you see. Then the angle in between these ones is going to be 120 for trigonal planar, you know that, okay? That is 120. Then what else? We also have these ones. So between the vertical and the horizontal, the angle is 90. You see that? So, but here they said that every bond angle is 90. So you see that this one is wrong because we have 120. Then part B, the central atom in the molecule does not have a lone pair of electrons. When you look at phosphorus, remember it is in position 15. We have 1s2, 2s2, then 2p6, you see that, then 3s2, and then 3p3. Now in here, what happens, since all of the 5 are used in the outermost shell of this phosphorus has gotten how many electrons? 5, okay? So it has used all of them. What happens is that one electron is excited from the s, okay? So one electron is excited from the s, if this is the s orbital, then the p here, then there is a d shell here, 1 2 3 4, because for it it gets a maximum of 10, okay, 10 electrons. So there is 1 electron here. Remember this one initially had how many? 3. Then this one had 2. Now this 1 electron is excited from the s orbital and then it is put to the d. Now these are 5 electrons that are ready for bonding. So that's why you can find phosphorus when it uses all the 5, or it uses only these 3 and there is a lone pair here. So in actually phosphine, if we have something like this, it will be this, then you get the 3 here. For this one, it will have a lone pair, but here it has used that lone pair also here. So they are saying that the central atom in the molecule does not have a lone pair of electrons, and indeed it is true. We have not seen a lone pair of electrons because this is hybridization, okay? So there has been an excitement of electron from the s orbital to the d orbital, okay, to use all the 5 electrons. It is not like this one where there is a lone pair and then the structure is going to be what? A trigonal pyramidal, you see? So meaning that our answer might be this B here, but let's check C. The molecule has an overall dipole moment. Now, since you see these ones here on the horizontal, it is 120. They are in that triangle. So it is this, that, and that. And the angle is the same here, all through 120. And they are what? They have the same dipoles, okay? Because this one Fluorine is electronegative, so it tends to pull bonding electrons towards itself. Okay, even this one does the same, even this one does the same. You see, so there are three around it, and they are distributed equally, okay, around the phosphorus. So there is not going to be a dipole moment. Remember, even these ones that are vertical, they cancel out. This one takes here, so they cancel out. Okay, so C is also off. The shape of the molecule is octahedral, because this is wrong. Octahedral, you must have 6 bonds. Okay, so you have this, you have this, you have this, you have that on a square. Okay, then you will have one here and then one here. So that is not the case for this molecule. So that's why our answer is what? Is D. Question 12. Which solid compound has both ionic and covalent bonding but not coordinate bonding? So if there's a covalent bonding, there is sharing of electrons, which is the same for coordinate bonding, but only that the electrons here in coordinate bonding are coming from one species. Okay, that one we see it in this dimer of aluminium chloride. So you have aluminium here, you have another one here, you have chlorines, okay, and there are 6 of them here. So we have these bonds established here. Now aluminium has 3 electrons, so those are the ones it is going to share with the what? With well, there is a mistake here. This one has to be yeah, there is this and that. So it is going to share with the chlorine, but then because of the high charge density, this one, I mean, there is this aluminium is going to be electron deficient. Okay, so what happens is that one lone pair of chlorine, okay, one lone pair in chlorine here is going to be shared with this, so you find something like that, and also this one will do the same, and it gives here they share. So this is coordinate bonding here. You see, sometimes you find when the arrow is here, okay, and then the other one is here. It doesn't matter. So that is that. Here there is coordinate bonding. Okay, there's coordinate bonding, so this one is off. Then we go to B. When you look at this one here, you have CH3, CO, then O. There is a minus here, then Na. So this is ionic bonding. You see, we have the oppositely charged what? Ions coming together. That is ionic bonding. But when you look at this ion here, hydrogen and carbon are covalently bonded. Then carbon and oxygen are also covalently what? Bonded. So here there is ionic bonding, and then also in here we are seeing covalent bonding, and there is no coordinate bonding. That means our answer is B. When I come to this one, this is ionic bonding strictly. When I come to this one here in ammonium chloride, ammonium as an ion, and then this is the chloride. So these are 2, that is ionic bonding. But in here, the ionic bonding, this ammonium ion is formed from here. You have ammonia, it has a lone pair of electrons, then it is donated to the proton. So these ones are sharing electrons. Okay, when they are sharing electrons, nitrogen has given its 2 electrons to this hydrogen here. So that is coordinate bonding. The structure even is going to change to go to tetrahedral. Then here it was what? Trigonal pyramidal. You see? So here there is, first of all, covalent bonding, sharing of electrons, but there is coordinate bonding there. Then there is also ionic bonding, but remember they said not coordinate bonding, and yet we have seen it here. So D is also off. That's why our answer is what? B. Question 13. Which equation represents the standard enthalpy change of formation for ethanol? Now for standard enthalpy change of formation, we look at 1 mole of a compound which is formed from its elements, okay, under standard states. So for ethanol, ethanol is a liquid. So wherever there is a gas, we are going to put this one off. It is here or here. It's a liquid at room temperature. Then we also look at now it is formed from carbon, hydrogen, and oxygen. So we can see carbon, which is a solid, hydrogen, and oxygen. All of them are in their standard states. But let's see the balancing, if it is okay here. 2 carbons, 2 carbons. Yes. Here, we are having 2.5 now times 2, which gives you a 5, not so? But this way, hydrogens 5 and 6. Do you see that? So the hydrogen atoms this way are 6, and yet here it is 5. So that one is enough to disqualify B. You see that? So that means our answer is D. But let's check. It is balanced. This is 5 and 1. That will be a 6. So we need 3 moles of hydrogen here. Then a half of this oxygen here to give us 1 here. Okay? A half of the 2 to give you 1, which is here. Then 2 carbons, 2 carbons. So that is the balanced one. We are forming 1 mole here of a compound in its standard state from its elements. The elements, we can have many moles as we want. Okay, but are they in their standard states? That is the question. You see that? Question 14. When potassium, this one looks like potassium permanganate, but it has 2 here on the potassium. Let's find the oxidation state here. So if you have N, we have 2 for potassium. That one is going to be 2 times 1 because each of them has +1, then +4, and then for oxygen it is -2. Then we equate to 0 because this one is not charged. So this will be 2, then -8, that will be -6. So meaning when we take the -6 the other side, then this one is going to be +6. So this one is going to be potassium manganate 6. Okay, so when potassium manganate 6 reacts with concentrated hydrochloric acid, the products include chlorine molecules and manganese 2 chloride. Manganese 2 chloride. All of the manganese atoms are reduced to manganese 2 chloride. So meaning in here, the oxidation state of manganese is a +2. You see that? Then they are saying both manganese and chlorine change their oxidation numbers during the reaction. Okay, no other element is oxidized or reduced. Now, that means when I'm writing this equation, I will have this potassium manganate 6 plus the concentrated HCl. I would expect to get what? Chlorine molecules. That's what they said. Chlorine molecules, and this chlorine is diatomic. Okay, then plus I would have put this one here, but they said that all manganese atoms are reduced to this one here. So in here we're having a +2. Then what else? They said something here. Both manganese and chlorine change their oxidation numbers during the reaction. Now, when you look at here, the oxidation state of chlorine is a -1, then here is a +1. The oxidation state of chlorine in here, it is going to be -1, okay, for manganese 2 chloride. Now, here, it means that chlorine has not changed the oxidation state. You see that? So instead of writing this one here, I'm going to instead write manganese 2 plus here, okay? Those other chloride ions, maybe they will turn to the chlorine. And by the way, we don't know many more that are coming forth, okay? Many more products. You get it? Because there is oxygen here, there is potassium, okay, there is hydrogen here. Maybe there is what? Potassium hydroxide or potassium oxide, there is water, something like that. We don't know. So, but our focus is on these ones here, okay? Now, when you put manganese then chloride, like the way it is said here, you are going to, like I said, you are not going to see the change in oxidation state. So this one is -1, and also this one will be -1. So there you will be failing. Okay, so we are going to consider this one here. We don't know the products that are coming forth. Okay, so let's look at, first of all, the oxidation state here. We found it as +6, and then here, of course, for chlorine is 0. This is -1. Then this is 1, +1, +1 here, then -2, and then this one is a +2 here. Now let us look at the change here. From 6 to 2, the change is a 4. So there is reduction there. That's why they even say all atoms of magnesium are reduced to this one here. Now, that means I'm going to have a 4 here, and then the change here is a 1. You see that? After that, because it is from -1 then to the 0, so the change is a +1. Now, we are going to get this change here. I'm not going to put minus, okay? We know that it has reduced, but by 4. Now, we get the change here in the oxidation state of manganese, where manganese is. Then we switch it and then multiply it here when we are balancing the equation. We switch it here where there is oxidation number change now for chlorine. So meaning I will put a 4 here, and when I put a 4 there, this simply implies that the chlorines are for this side. Now when we come to this side, here they are 2. So I will not put a 4, because this 4 that I get, I'm supposed to multiply it in here. So I multiply it here and here. But now when I put a 4 here, don't you think chlorine atoms are going to be 8? Yes, so that means we put a 2 here to balance that. So this will be 4, and then this is 4. You see that? Then after that, we shall put a 1 here and here. This is the oxidation number change for chlorine here. So we multiply it where we see the oxidation number changes for manganese. You see that? Then from there, we don't know whatever is coming forth. Now we can balance the rest, but these ones have to be like this. Okay? All right. Now let's continue. They are saying, using these changes in oxidation number, how many moles of chlorine will be produced when 1 mole of potassium manganate 6 reacts with an excess of hydrochloric acid? We have seen if it is 1 mole, it is producing 2 moles of what? Of chlorine. So that means our answer has to be A here. Question 15. A nitrogen-hydrogen mixture, initially in the mole ratio 1:3, reaches equilibrium with ammonia when 50% of the nitrogen has reacted. The total final pressure is P. What is the partial pressure of ammonia in the equilibrium mixture? Okay, this is what we are going to have. First of all, you have nitrogen here reacting with hydrogen to give us ammonia. All of these ones are gaseous. Okay, that's why we are dealing with partial pressures. So the pressure each of these ones exerts on the what? On the walls of the container. Now, initially at T is equal to 0, we have 1 mole here and then 3 moles here. 1 to 3, you see that? And then this way you have 0. Now something reacts off here. Okay, something reacts off here, but then this way it comes as twice of it, because you see this is 1 mole and this is 2. Do you see that? So it reacts off here, but then this way it comes there as a double. Okay, now that same reaction, that same amount of moles that react, here we shall say 3, then minus. This is 1 to 3. So if X has reacted off here, then here we shall have 3X reacting off. Do you see that? But they said that when 50% of the nitrogen has reacted, so here we shall have 1 minus 50% of nitrogen. So you have the 50% of this one that you're having here. You see? Then here we shall have 3 minus, then 3 times the 50%. You see that? Just like here we have the X and then the 3X. meaning this way you'll have 2 then times the 50 what percent. 2 times 50% of what? Of the nitrogen, the moles of nitrogen. So that means here we're having 0.5, then here we shall have 3 times, this will be 1.5, so 3 minus 1.5, you get 1.5. Now this one will be 0.5, then times 2, that one will give us a 1, okay? So meaning the total number of gas moles, total number of moles is going to be 0.5, then plus 1.5, then plus 1. This one will give us a 3, okay? Then the partial pressure of nitrogen, that is the one they have asked us to find, actually of ammonia, not nitrogen. So we are going to get the moles of ammonia at equilibrium, which is 1, then divide by the total we have gotten, then times the total pressure. And they said the total final pressure is P. So times P. That means our answer is C here. Question 16. Propyl methanoate is hydrolyzed with aqueous sodium hydroxide at 20 degrees C to form two products, X and Y. Product X is an alcohol. Data from the experiment is shown. Every after some seconds, then we see what is being formed here. Remember, rate of a reaction, we look at the rate at which the product is formed, or the rate at which the reactant is being consumed. You see that? And X is a product, so these are the ones that are being formed every after some time. Okay, which row is correct? Now here I'm seeing average rate between 240 and 300 seconds. So average rate, how are we going to get it? Average rate is going to be equal to from 240 to 300, we are here. So that will be 0.022 minus 0.18. Actually, it is 0.019. So what was added here? Which change was here? The which concentration of X was produced within this time? That's what we are trying to find. And then we have to divide by the time. So that one, the time taken is 300, then minus the 200 and what? And 40. 0.022 minus 0.019. Then down we have 300 minus the 240. This one will give you 5 times 10 to the power of negative 5. This will be moles per liter, okay? Because that is the concentration of X, but then we are dividing by time, which time is given in seconds. So it will be per second. You see that? And when I look through the answers here, I can see it here and here. That means these two have to be off, okay? Now let's go to the products. Now when you hydrolyze, because this is what we call alkaline hydrolysis of an ester. So you have this methanol, this propyl methanoate. So we have the carboxylic acid is methanoic acid, not so. Then CH2, the alcohol, then has to be propanol, then CH3. Okay, so here we are going to add sodium hydroxide and what? Water. You see? So what do we get? Water will come and break this one here. This one will take its OH it lost in the reaction, and then this one here will get its hydrogen. Okay, now when we put them there, you will have this methanoic acid first of all, then plus you'll get this alcohol here, CH3, CH2, CH2OH. But now this is an alkane. I mean, this is an alkali. So this alkali here is going to react with this acid here. So instead of you getting the acid here, you will get a salt. Okay, you will get a salt. So this one will give us, I'll put here that one there, you see, and this one will be dissolved in the water because there is water also here, you see. But maybe I'll just write something like this, like these ones here. I'll put them on the arrow. In fact, we can do something like this. We say aqueous sodium hydroxide, and we get this. So we get a salt instead of the acid. If we had used the dilute acid, we would get the acid here, the methanoic acid, then plus the alcohol. This alcohol, by the way, does not react with the sodium hydroxide. It only reacts with sodium as a metal. We give the explanation here in A level, okay? Especially when we are using phenol, because this one can react with acids. I mean, with alkalis, it can react with this one here because for it is acidic, but the explanation is in A level. So that means this is the one here. This is not this. So the answer has to be A. Question 17. The table shows the numbers of bond pairs and lone pairs in 4 different species. Which row is correct? So I'm seeing nitrogen, ammonium molecule, ammonium ion, and then hydroxide ion. Okay, so let's go to nitrogen molecule. Nitrogen has a triple bond. That means it has, how many electrons are shared? This one has 2, this one has 2, this one has 2. So those are 6. Okay, so numbers of bond pairs, these are 6 bond pairs. You see that? Then what else? And they also have a lone pair, by the way. There's a lone pair on hydrogen, on nitrogen. So total number of lone pairs. Total number of lone pairs, we are seeing 2 lone pairs, okay? One here and one here. That is for the nitrogen. But they said here the total number of bond pairs is 3. Actually, I made a mistake here. These are 3 bond pairs. Pardon me here. 3 bond pairs. We are having 6 electrons, but this is a pair, this is a pair, this is a pair. Okay? All right. Now, total number of lone pairs, they are saying 1, but we are seeing what? 2. 1 here and then another one here. So this actually disqualifies A. Then we go to ammonia molecule. Ammonia molecule here, it has a trigonal pyramidal shape. Then here there is what? A lone pair. So this is a bond pair, and a bond pair. So these are how many? 3 bond pairs and then 1 lone pair. So the 3 and 1 would have been for this one here, but they are saying 4 and 1. So that means even this one is off. Let's go to the ammonium ion. Ammonium ion, now this one donates a lone pair to a proton. You see that? When it donates a lone pair to a proton, we are now going to have a tetrahedral shape now formed here. Using valence shell electron pair repulsion theory. So there is a bond pair here. How many bond pairs? There are 4. 1, 2, 3, 4. The lone pair is out, but it has given us a what? Now a bond pair here. So there are 4 bond pairs and 0 lone pairs. 4 and 0. This has to be then the answer. Okay, but let us check out the hydroxide ion. The hydroxide ion here is OH. So there is a bond pair here. Okay, and then the lone pairs. How many lone pairs does this one have? We are going to see this one has received an electron. Okay, so if it has received an electron, the minus is there. So it has how many electrons? 1, 2, 3, 4, 5, 6. Not so? So the lone pairs, these are 3 lone pairs, then plus what? one bond pair. So that's why even this one is off. So our answer is C. Question 18, which row is correct? Then the first one, they are saying the property is silver iodide dissolves in aqueous ammonia more readily than silver chloride. No, actually iodide ions are insoluble in aqueous ammonia and concentrated ammonia. Chloride ions are soluble in dilute ammonia and then concentrated ammonia. Then bromide ions are sparingly soluble, or we can say insoluble in dilute ammonia, but in concentrated ammonia they are soluble. So this one is wrong. I don't even need to look at this side. Then we go to B. HCl decomposes more readily than this hydrogen iodide. This one is also wrong because we know that bond energy decreases as you go down the group. Okay, why? Because this one is a shorter bond compared to this one for iodine. Okay, because this one is very big in size. Of course, hydrogen is very small, so this is small and small. So the nucleus is far away from this bond pair here. Okay, for iodine. So the nuclear attraction for these electrons is weaker. So that means this one is going to be a longer bond, and therefore we are going to get what we call a longer bond. So the longer the bond, the weaker it is. So this one has to be off. Okay, I don't even need to look at this one. But we know, yes, chlorine is more electronegative than what? Iodine. Okay, but still, that is not the explanation for this, which is already even wrong. Then see, iodine has a higher melting point than chlorine. This one is correct. Why? Because for these metals, as you go down the group, you are going to increase the number of you are going to increase the number of electrons, and the more the number of electrons, then the stronger the ID what forces. So here they are saying iodine has stronger van der Waals forces than chlorine, and that is right. And when we are explaining anything to do with melting point, one, we look at the structure and bonding. All of these ones are simple molecular. Okay, then next we go to the strength of the bonds, strength of the forces, the intermolecular forces. So here we are using van der Waals forces, or you can call them the ID forces, right? And here they are stronger in iodine because of the many electrons compared to the chlorine. You see that? So therefore, our answer has to be a C, because this one is also correct. Now here, iodine is a stronger oxidizing agent than chlorine. When you go down the group, first of all, these group 7 elements react by gaining an electron. Okay, but to gain an electron, when you look at iodine, this nucleus is far away from the outer shell of electrons here. So this incoming electron, because of the much shielding that is coming from the inner electrons here, it makes the nuclear attraction for the incoming electron weaker. You see that? So it is not easy to gain an electron for iodine. Instead, it is easier for iodine to lose. And yet these ones are supposed to react by gaining an electron. You see that? To gain an electron, that means you are getting reduced. That means you are an oxidizing agent. So chlorine is a stronger oxidizing agent compared to iodine. So iodine can easily lose the electron. That means it becomes oxidized. Not so? And something that gets oxidized is a reducing agent. So iodine is a better reducing agent, and chlorine is a better oxidizing what? Agent. So when a reducing agent finds an oxidizing agent, they are going to react. So that's why chlorine is able to displace iodine from the reaction, from the aqueous solution. So that is that here. So this one is out. Okay, I don't need to look at the explanation. Question 19, substance J reacts with water. A gas is given off and the pH of the solution increases. That means here we are getting a hydroxide. Then the solution is then reacted with sulfuric acid and the white precipitate forms. Then they say, what could be substance J? Let's look at barium first here. So if I get barium, then I react it with water. This one is a solid, then plus water. Yes, group 2 elements react with water to give us a hydroxide. So that is barium hydroxide here, okay, which is more soluble. So I can put aqueous here, then plus what? Plus the hydrogen as a gas given off. So this one will be 2 hydrogens and 2 hydrogens. That one makes it 4. So I'll put a 2 here, then oxygen 2, oxygen 2. That is the one here. Now, in group 2, the solubility of hydroxides increases down the group. So this one is more soluble. So that means it is going to be barium ions here. It is going to split into barium ions, okay, and the OH ions. Now, because of the presence of the OH ions here, that is why the pH of the solution increases. Do you see that? Now, when you react this with sulfuric acid, automatically the barium ions here are going to react with the sulfate ions. Then from here, you get this white precipitate, which is barium sulfate. And we know that solubility of sulfates of group 2 elements decreases down the group. So magnesium sulfate is more soluble than barium sulfate. Barium sulfate is not soluble. You are going to see it being precipitated out. You see? So that means our answer actually has to be A. But if you get barium oxide, you react it with water, you will just get barium hydroxide. There won't be a gas produced. You see that? Then when we go to magnesium, we shall get this magnesium hydroxide and hydrogen. But when you get magnesium here and you react it with the sulfate, that one is soluble. So you are not going to get the white precipitate. Then magnesium oxide, you react it with water, you will get just a hydroxide, but no what? Hydrogen. So that is why our answer is what? Is A. Question 20. Compound L has empirical formula NH. It decomposes on gentle heating to produce ammonia and compound M only. An aqueous solution of compound L is a good conductor of electricity. Now, for conduction of electricity, we look at free movement of ions and also electrons. That is like in the metallic structure. And the ions that are known for the highest conduction of electricity are hydrogen ions and the OH ions, okay? Now, let's see what we are having here. Now, when you get a salt of ammonia and then you warm it in a solution of an alkali, let's say a strong alkali like sodium hydroxide, ammonia is always given off, okay? So they are saying it decomposes on gentle heating to produce ammonia and compound M only, okay? To produce ammonia, that means we must have ammonium ions in L. So when you look here, we have ammonium ions here, okay, and also ammonium ions here, you see. So when you get ammonium ions, by the way, that are in that salt, maybe it is ammonium chloride, whatever, then you add an OH, okay, you are going to get ammonia given off, and then what? Water. This is an acid-base reaction, okay, because the proton is donated to this, right? So that is what we get there. Now, we have to look at these two. Which one is correct? These ones, we shall just take them off because there is no ammonium what? Ion. Then, compound M. An aqueous solution of compound L is a good conductor of electricity. When you look at these two here, okay, which one is a good conductor of what? Electricity. Okay, right from also where? And then M, they said that it decomposes on gentle heating to produce ammonia and compound M. So suppose I get NH4, then N3, okay? On gentle heating, it decomposes on gentle heating to produce ammonia. Okay, so this is just heating it, okay? Here I was saying when you use or you warm it with an alkali, that is when you get the ammonia. Now here we are going to get ammonia, okay, and compound M. So here we are seeing compound M, so suppose we write HN3. Then there is also this one here for B, NH2, something like that. Then we get ammonia, then plus compound M. What is compound M? Now for them they are saying N2, then H4. This is our L. Then this way we are having what? M, okay? Empirical formula. This one here, first of all, the molecular formula here is going to be N2, then H what? N2, then H6. Are we there? Because these are 4 plus the 2. Then, this is the molecular formula. Then empirical formula is going to be what? Empirical formula is going to be N, then H3. Okay? Like that. Then, when I look at this one here, which I got from, I think, option D. So this one already fails. This one fails. Why? It's because the empirical formula that I'm getting from here is NH3, and yet they said NH. So when we come to this one here, what is the molecular formula? This is N4, then H4, and then empirical formula is going to be divide all through by 4, so that will be NH. So this one gives us, so that means our answer has to be D.